Hey everyone, my name is Dan Votipka. I'm a PhD student at the University of Maryland, and today I'll be talking about some of the work that my colleagues and I in the Security, Privacy, and People Lab and the Programming Languages Lab at the University of Maryland have been doing, trying to understand the security mistakes that developers make. So, if you look at the NIST's Common Weakness Enumeration reporting over the past few years, you'll see that there are several vulnerabilities that we consider solved. The developers still introduce. And by solved, we mean that the developer could have chosen a different language or API or something like that that would have just mitigated the problem for them. There's actually a solution available. This includes things like buffer overflows, improper access, or information leakage, improper access control, and cryptographic issues. Um, and so you might be asking yourself, well, why do developers continue to make stupid and lazy mistakes? But we argue this is actually just the wrong question to ask. Instead, we should be asking, how do we make programming easier? Uh, so there's several possible solutions you might think about. Well, better education, better APIs, better documentation, better tools, and on and on. But really, the question we wanted to ask is, well, how do we actually improve the effectiveness of these solutions? Um, And in order to do this, we really need to understand the types, causes, and pervasiveness of the vulnerabilities so we can match the right uh, mitigation or the right tools to this problem. So you might ask then, well, how do we actually measure this? Well, um, when deciding what method to use for this type of study, we're really working on a spectrum from ecological validity over to control over the conditions. And there's several methods that you might choose depending on sort of the research questions you're asking, with things like field measurements, going and pulling data off of GitHub, or going and actually embedding in a company and performing observations there, which will give you a lot of really great ecological validity. You get to see really what's going on. You see code that's produced in a real world situation. But there's not really any control over that, so it's hard to understand causality from it. And on the other side, you have lab studies where um, you bring a participant in, they're performing a given task, so you have a lot of control over that, so you get to causality, but these tend to be smaller programs that they're working on and don't necessarily represent what you'd see in the real world. And while both of these, as we said, are valid approaches to use, we decided that we wanted to take sort of a middle ground approach with the introduction of the Build It Break It security competition, or Build It Break It Fix It secure coding competition. And so the way Build It Break It Fix It works is that we have teams of participants work together to build a program of medium size over the course of a few weeks. And they're given several incentives to think about functionality, performance, and security. And so in the first round, in the build it round, teams build according to a spec. We give them several different functionality that they're supposed to implement, as well as a threat model to consider during this process. And they get points depending on how much of the functionality they provide and how performant their code is. And this chart here just shows one of the competitions, each of the teams, the language that they used, and their sort of score as it moves. And then in the second round, in the break round, teams are given access to each other's code, and they go in and try to find vulnerabilities. They produce exploits against them. And then finally, in the fix it round, teams are allowed to go back and fix some of the problems that were identified by other teams in their code. And if you want a specific look at how this all works, you can see our CCS paper from 2016 that goes into the details of Build It, Break It, Fix It. But this provides a nice sort of middle ground where teams have to consider sort of real world things like functionality and performance, along with security, and they're working on larger code and teams. They get to pick their language, but they're all working on the same problem set, and we can adjust the incentive structure to add different controls in. So we've run this over 4 years, over 3 different problem sets: secure file storage, network communication, and an access control problem. And so we wanted to look at this and see, well, what were the types of vulnerabilities that developers actually introduced here? We also looked at how severe the vulnerabilities were and how exploitable they were. But for brevity, I'm only going to talk about the types of vulnerabilities introduced in this talk. So to analyze this data, we had researchers go in and actually look at the projects and looked at all the exploits that were submitted against them. to try to understand what the specific set of vulnerabilities were, both that teams found as well as those that they didn't find. We go in there and perform an additional security review. And we did this review of all the vulnerabilities that we introduced. We performed an iterative open coding, where two of the researchers independently labeled all of those vulnerabilities, and then we compared them until we reached a high level of reliability. And we performed this on a sample of 94 projects with 866 submitted exploits for those projects. And that ended up being about 182 vulnerabilities from both these 866 submissions as well as ones identified by the researchers. And so we performed this qualitative analysis to identify all the vulnerabilities and code them. And then we performed a quantitative analysis on the resulting data to determine the prevalence of those problems. So what do we find? What types of vulnerabilities developers introduce? Well, we actually found that they could be grouped into sort of these three main classes with subclasses. So first, the no implementation class. Here, the team just didn't implement one of the security mitigations that was required given the goals that we set out for them in the specification. This is broken into two subclasses. First, the intuitive class, where teams just didn't implement something intuitive. For example, in the secure file storage problem, they didn't implement any encryption, or in the access control problem, just not providing any access control. The other subclass here is they didn't do something that was sort of not obvious from the security goals. So things like for the secure file storage, not including an integrity check. So they might understand that it needs encryption because it can otherwise just be read. The file can just be read by the attacker on the device in plaintext, but they might not understand that it needs an integrity check. The network communications problem, we also saw issues with side channel leakage and replay protection, where replay prevention would fall into this category. And the next class of vulnerabilities, teams actually tried to implement one of these mitigations, but had some kind of misunderstanding. For example, they might make a bad decision about the library or algorithm they used, picking something that was known to be insecure. So for the secure file storage problem, this would include things like using a weak encryption algorithm or trying to roll their own encryption, or taking in input using stir copy as opposed to a bounded copy. The other subcategory here is that they actually used a reasonable algorithm or library, but they made some error in the implementation. This could be things like using a fixed value. So going back to that secure file storage problem, they picked the right encryption algorithm using AES, but this team actually used a fixed value for their initialization vector. And actually, if you go to Stack Overflow, you'll see that this is actually an example of what we think is one of the team just copy and pasted this code, fortunately. Other examples of this include lacking sufficient randomness. So for example, if you were trying to provide a nonce to prevent replay protection, having that nonce overflow after a short period of time, or disabling protections in the library. So as an example of that, one team actually had a really elegant approach where they used this SQL Cipher library that just handled all the encryption and the integrity checks for their file storage for them. But to provide more performance, the team realized that they could turn off per-page integrity checks. And when we looked at their Git history, we saw that they did this for performance purposes because they thought, well, these are per-page integrity checks. I have a full-page integrity check I assume occurs, so I'll just turn off the extra ones and we'll be good. Well, actually, this is the only integrity check, and the team was attacked and lost a ton of points because of this. And actually, if you go look at the documentation, it's very unclear that that is the case. If you read the documentation, it's very it makes sense that the team made this mistake. Okay, so the final class is these mistakes, and this is basically just the team does something like make a control flow error, putting a not in the wrong place so the control goes the wrong direction, or skipping a specific step in the algorithm where they do everything right except for one step. And it just looks like they forgot something small, not a overall conceptual problem. So which of these were actually the most prevalent? Well, these numbers show the percent of teams that actually had these problems, and you can see that mistakes were the least common. And actually, we performed statistical tests and showed this is actually statistically significant these were statistically significantly least common. And actually, when we looked at what teams did things like or perform best practices, like not copy and pasting all of your security checks all over your code base, but only having them in one place, that also reduced the number of mistakes. And in addition to that, all of the mistakes were identified during the breakout round, except for one, meaning that code review is likely helpful in preventing these. Now, looking at the other sort of subclasses, we found that the teams, in most cases, were able to identify the intuitive mitigations that were necessary, but not all of the unintuitive classes, and that they were, in most cases, picked a reasonable algorithm, but made some mistake in its implementation. So for recommendations, we recommend that API design be simplified as much as possible, building in the security primitives and for common use cases, because teams or participants are able to identify what the mistakes are, or sorry, they're able to identify basic security mitigations they need, but they might not know all the requirements. It's also important whenever developers go beyond sort of these defaults, the documentation clearly states what could go wrong or what the security consequences are, explaining these negative effects for turning off certain things, for example. And finally, when it comes to vulnerability analysis tools, more emphasis needs to be placed on sort of these high-level design conceptual issues. So in summary, we know that developers struggle with security concepts. We know that mistakes happen. They produce through code review and best practices and provide some conceptual, or we provide some recommendations for how to avoid some of these problems. So with that, I want to thank our sponsors and thank you all for your time, and I look forward to answering all of your questions.